Okay, so let's talk about contingency tables. This is a way that we analyze data that's not continuous. What we did last time with our interval and ratio data, right? We can't do that with nominal and ordinal data. I think everyone understands why, right? We looked at that before. But we can still kind of describe the relationship between the variables. And I just like to put stuff like this here because it helps me understand why it's called a contingency table. It's because the dependent is contingent on the independent, right, variable. So it doesn't matter that it's also called these things at all. It's really important that you know that we put the independent variable in columns and the dependent variable in the row. If anybody has epidemiology at the same time as this class, it's the opposite of what you do in epi. So it can really mess you up. Does anybody have epi right now?
No.
Oh, good. Okay. So then just scratch that. So yeah, just make sure that you read the question properly. You need to identify the independent and dependent variables. Otherwise your chart will come out all wonky. Again, I just said that. You're reading it backwards. None of this matters. So,
sorry.
Yeah, whoever that is. Some research questions you can actually reverse them. So the dependent and independent can go either way. For example, does income level affect education, or does education affect income level? Quite frankly, you shouldn't have the word affect in a correlational question, but whatever. They're just saying it goes either way. So you can decide whether you want to put which one's independent, which one's dependent, where you want to put it on the chart, depending on how it's phrased. And I think you'll see that in the assignment. It kind of goes through that, hey. So great, we have this table here that gives us like these counts, right? You know, there are 42 male dogs, 10 male cats, for a total of 52 males, you know, and so on. But that's just kind of like putting numbers in a chart, right? How do we find if there's any kind of correlation or statistical value? Sorry, can you hang on 1 second, guys? What's up? Yeah. Yeah.
Is there anything else?
Okay. Wine. Some wine. Sorry, guys. Honestly, like I said, it's total chaos here. We've been working on my son's Halloween costume for like, I don't know, like 100 hours. It's just been ridiculous. I didn't sleep last night. We finally got it done and sent him out. And anyway, so that doesn't matter. So your correlation, this is how we're going to kind of measure the relationship between the variables. Again, when you see correlation with your R, right, your correlation coefficient, this is not experimental. When we're talking, this is just, how does this thing relate to this other thing? It's not, you're not doing any intervention. There's no control. This is not like a RCT. This is just, is there a correlation between income level and education level, right? So your Pearson R, or not your Pearson R, don't see, I'm going to screw up. Your R, the correlation coefficient, that's what we're calling it, tells you how strong the relationship is between those two things and which direction it's going in, which direction the relationship is. So you can have your positive and negative. We'll go through that later. What you want is a perfectly linear relationship where as one goes up, the other goes up, and they keep going up together in equal measure. That almost never happens, but we want the closest we can get to that straight line. And I think there's a chart down here that kind of, yeah. So if you have, you know, an imaginary line going right here, these are actually almost perfectly, you know, as this is going up, this is going up, this is going right. You'll see it better later. It's just blobby there. So we use, see, I don't like the way they taught this. So the correlation coefficient is just a number that represents the direction that a relationship is going in and the degree or the closeness or how close it is to a linear relationship between those two variables. You use this when you're interested in direction and strength. You have one sample group with two variables usually. You have continuous data. They're doing this. It's represented in a table or a scatter plot, which is what this thing is down here. Okay, so what helped me is, remember up here we said whenever you make a chart, a contingency chart, the independent variable is in the columns, dependent is in the row. It's the same when you make the chart in terms of direction. So when you make one of these scatter plots, which we'll hopefully figure out how to do. I seriously can't remember, but hopefully we will. Your independent variable is going to go horizontal, same as it went on the top of that chart, going this way, horizontal. And then your dependent is the same. It's going up, it's going vertical, up and down. Same as on the other chart, it went in rows. So that's kind of nice because it's at least consistent that way. So when we're looking at correlational data, right, that and that's what R is measuring, right? It's measuring a correlation. How strong is that correlation? How, I know I'm repeating myself, but how strong is that correlation? What direction is it going in? So there are these characters that we use to describe the relationships. It's a positive relationship if the two variables are changing in the same direction. If X goes up and Y goes up, if X goes down, Y goes down. So people get confused about this a lot. And they say, oh, X is going down. Like my first variable is going down and my second variable is going down. So it must be negative because they're both going down. But no, if they're both going in the same direction, they're positive. If they're going in the opposite direction, so as X goes up, Y goes down, then it's a negative or it's an inverse relationship. Does everybody get that? There were just some problems last time with the positive and negative, but everyone's good with that?
Lauren, what does the plotted points look like when it goes down? Like if they're both like going down positive?
Like this.
Like that? Okay.
Yeah. Like, so it's that easy that you know, the line is going, you know what? I'm pretty sure. Sorry guys, to be honest, this is like, I haven't looked at this in so long. So we're talking about the relationship between coffee sales and temperature, right? Here's your coffee sold. So we have, you know, 10, blah, 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 and temperature in degrees. So as the temperature is going up, right? So you've got, this here is, it's 60, selling 60 gallons when the temperature is 20. When the temperature goes up to 30, you're only selling 50. When the temperature goes up to 40, you're only selling, right? So the temperature is going up, but the amount of coffee is going down. So it will look like this. If you've got the opposite here, I hope I'm not like over explaining this, but you've got your amount of beer and your temperature. When it's 20 degrees, you're selling, you know, it's 15 or some odd, I guess, gallons of beer. Sounds good right now. 30, as the temperature goes up to 30, this is weird, but let's use this dot. 25, right? So as the temperature is going up, the amount of beer is going up. And because you always put your independent and dependent variables on the horizontal and vertical axes properly, then whenever you have a positive relationship, it's going to literally look like it's going up. And when you have a negative relationship, it's going to look like it's going down. If you screw up these axes, that won't be true. So I wouldn't rely on, you know, what the graph looks like to make your decision. You should like think it through. Okay, well, the temperature is going up and the coffee is going down or whatever. See, we get it. The straight line. So we're not going to worry about the curved lines. Thank God. I don't even want to think about it. So we're talking characteristics, right? And the first one is direction, whether it's positive or negative. The second one is the degree to which, how close those things are to matching perfectly. Remember I said, you know, if they go up exactly on the way, oh, you guys can't see me. I'm totally making hand gestures. Like they go up together all the way up perfectly. That's, you know, your perfect linear example, I guess. I think there's actually a name for that line of, you know what, I don't know. And so if your, let's do this one here. If your temperature and your amount of coffee sold, if it was a perfect linear relationship, all the dots would be on this line, right? And that would mean that would be an R of 1. Okay. So, okay, I'm just gonna wait for the phone to stop ringing. And so that doesn't happen very often, right? If you come out with a 0, and I think I have a picture of one. Yeah, here's one here. No relationship at all, right? There's no, you can't even draw an imaginary line. Like, which direction is that going? I have no idea. There's obviously no relationship between Y and X here, right? And so in that case, it would be an R of 0. So that R is telling you how well the data fits that perfect line. If it's perfectly correlated, you're going to get a score of 1. It can be negative or positive depending on the direction. So in this case, this would be a negative, probably 0.85 or something. And this one would be a positive 0.775. And we'll go through that a little bit later. So whether you have a -1 or a +1, it's still a perfect correlation. The negative doesn't negate. You kind of have to like get that out of your mind that negative is, I guess, like a bad thing. And so you're going to have numbers that are going to come out between 0 and 1. So you're going to get 0.85. And you guys have seen this before, right? The R, when you're looking at some studies, I think in research, they talked about that, about where your correlation coefficient should be, how strong that should be. So if you know, I get this here, this is a pretty strong relationship. They're actually fairly close. Like it really probably would be a 0.8, 0.85. I mean, I don't know, but it's really, really important, right? Because you need, the stronger the relationship, the more you can make inference from it, which actually you shouldn't with correlational data, so it doesn't really matter. Again, here, this is just saying what I already said. Here's a perfect inverse or negative. This is a perfect -1, R -1. And here's a little chart here. So use this if there's a question asking you, you know, whatever, if you have to describe it in words, you would say there's a very strong correlation between the two if it has a 0.8 or higher. Okay. Oh, look, here we go. Was that Christina that was asking that? Yes. Yeah, here, these are really great to look at. So when you have, this one's an R of negative 0.9, how close together all those dots are, they almost form a line on their own. And it's negative because look, it's going this way. Again, you still want to double check that with the data, right? Here you've got no correlation whatsoever. Don't worry about this because it's not going to come up in our work at all. And then here you've got a positive correlation, but it's a bit weaker, right? They mark it as a 0.4 to see that they're a little bit more spread out. There we go. There's the Pearson. Okay. So there are different forms of correlation coefficients. The Pearson R is the most common. It's a linear correlation. It compares the variance of the two variables. Don't worry about the fact that it's also called the Pearson product, blah, blah, blah. So here's the variance of the two variables, which is what you're looking at here. This is just the variance where they're all landing, right? I don't think you need to know any of this stuff. I don't want to overload. So remember we talked about in your measures of variability, you had that variance score, right? This is, and remember, I don't know if your prof said it or if I said it, that, oh, it'll come in later. You don't need to worry about it for now, but it's basically your standard deviation squared. This is how we calculate R. Thankfully, we don't have to do any of this math. So you don't really need to know this. I'm just going to skip it. It's just going to be really confusing. So R is about prediction. R is about using one variable to make a prediction about the other. Again, this isn't necessarily cause and effect, it's relationship. You can use it to test the validity of instruments, reliability, theory verification, blah, blah, blah. Only for interval and ratio data. Here's what's really important to know. When you're answering questions on your thing, it doesn't prove causation. It doesn't prove anything. It's basically these things are correlated. These things are related to each other, right? Okay, so in order for you to say that there is a correlation between two variables, you have to have all of these things in place. There's a linear relationship between X and Y. Yep. They're both continuous random variables. X and Y are approximately normally distributed. That's really important, right? And so how do you figure that out? You have to do a frequency distribution chart, and then you have to do the the histogram, and so that you can see that it kind of looks like this, right? It needs to be distributed. You can also figure that out by doing your descriptive statistics chart. X and Y must be independent, sure, and X and Y have roughly equal variability. This won't come up. This might, I don't remember if it comes up in the exam. You don't need to know it for the thing, but maybe for the exam. Don't worry about it for now. Whew. So, R squared. This is so we talked about correlation coefficient just being, it's measuring the characteristics of the relationship, right? This one, sorry about my spelling mistakes, tells you the proportion or percent of the variance of the dependent variable that is explained by the independent variable. Okay, so it sounds really confusing the way it's written. So in the other one, whereas we were talking about R is telling us the strength of the relationship, how strong is it? This one is telling you if, like, for example, let's take this. This is easier to, if you're looking at a correlation between the number of hours of sleep a student gets a night and their exam scores, right? And you have a positive relationship that you're seeing, and let's say it's a positive 0.7. Oh, here, look, I even said that here. So you get a positive 0.7, which is adequate. You want to take that 0.7 and you square it, which means comes out to 0.49. Just use your friggin' calculator. I suck at math, so I just use my calculator for everything. That's why, yeah, especially when I'm doing med calculations and stuff. So you've squared that, right? Some of you are brilliant and just did that in your head because it's pretty easy, but whatever. 40, and then 0.49 translates into 49%. And what that means is that 49% of the variable y, which is the outcome variable or the dependent variable, can be explained by the variation in the variable x, which is the income. So, which is the independent. So what they're saying here, yes, the relationship is adequate. There is a relationship. It's a positive relationship. As number of hours of sleep goes up, exam scores go up. It's, you know, an adequately strong relationship. 49% of exam scores, higher exam scores, can be explained by the fact that people got more sleep, which is kind of BS. That's impossible. But does everyone understand that? It's really important, and it can take a bit to kind of catch it. When you get to this question in the paper, like come back in the recording and just listen to that again, so that because I can't really explain it any better than that, but you can kind of go over it and make sure that you're understanding it. This we went over again. Unfortunately, the numbers are different than the other chart, of course. Of course. So it doesn't really matter. I believe this one is from the textbook and this one is from the slides. But it's basically saying the same thing, right? This is a high strength of relationship. This is a low one. Whatever. A mini tab printout doesn't look like that because this isn't Excel. Whoop. Okay, so Elaine said that do you guys do the cap? Is it cap? What are those videos that Elaine puts up for you guys?
There's a lecture one, and then there's also something called Captivate.
Yes. Okay. I'm not on crack then. It is Captivate. Did anyone watch the Captivate other than Marianne? No. Awesome.
Yes.
Yes. Okay, good. Because honestly, guys, I don't remember how to do some of the stuff, and we're gonna have to figure it out. But she says in that video, she says when you look at this, this R and P shows that it's not a good relationship, but she would explain later. So the Pearson correlation is 0.875, but the p-value, which we haven't talked about P yet, right? We're just doing R. Okay, so let's not get confused. Let's just keep going. So we explain correlation in a graph. A regression line shows the one-to-one relationship. This is what we were talking about earlier, that perfect line, if everything were exactly an R score of 1, everything would be on this line. Okay, that's just the regression line. Shows the tendency of the relationship. It can be used to predict what Y is likely to be based on what we know about X. So if this line keeps moving like this, we can make a prediction that over here would be up here. That's all that's saying. You don't need to worry about, it's also called the line of best fit. Okay, I thought that was true. I just didn't want to. So this is the line of best fit. Don't worry about calling it Y hat or predicted Y. Oh, wait, actually, sorry, you do need to know that. So this is a way of measuring how well the line fits the data. It determines the distance between the line. So you've drawn your line of best fit, right? And and the data point, right? So see, the distance here would be, I mean, we don't have measurement here, so it's really hard to do that. But your y hat or your y predicted y or whatever, it's just giving you, you know, how far away is this data point from the line of best fit. It talks a little bit more, I think, here. What we predict is also called the least squares line. It's drawn between data points and represents the least amount between the actual data and what we predict would be the line if the line were perfect. This is exactly what I just said. It's just said really wordily, and it's for some reason thought it was better. This line here too, when you guys do a scatter plot in your Excel, you can get this line, like there's a way to get it to show up on its own. You don't have to like calculate that yourself or figure it out or anything. It just, it'll show up. Whew. This is, I said this again. Square, make all positive, squared error predictions for each data. I don't think you need to know. I don't want to overload you guys, so I'm not going to do stuff that's not in the assignment, which hopefully it's not. Unless you have a perfect correlation, R regression line that predicts Y always has error in the line we have chosen as the best. Yeah, that's what I just explained. So you guys understand the reason we call this a best fit is because you don't have your data points aren't perfectly correlated, right? So it's the line of best fit, and there's going to be a discrepancy between that best fit and where your data points actually are. And like this one here has quite a, you know, this is quite a large, weird kind of outlier that probably if you took this one and this one out, this would be a much stronger correlation, right? So significance. So what we were talking about here is the strength of the relationship. The relationship can be strong, but not necessarily significant. And that happens when you're doing some kind of, you know, this is, let's say this is all your data, but literally like this is your number of participants. Well, sure, it's showing something, and your R may be strong. It may be that one looks like it's maybe 0.7, but it's not really a significant finding because you can't, you know, when you have a small sample, it's easy for it to look like there's a correlation when there isn't necessarily. And we'll talk more about that error. This is your error we'll talk about later. And again, you can have a weak relationship, but it's significant. So you have a really, really large sample, and when you, so this is hard to explain, and it probably won't show up in the assignment, but so it's a significant, even though it's maybe more spread out, like it's more spread out, but you have 100 dots instead of just these 10 or 15 or 20, however many are here. The fact that they're still moving in the same direction, it's actually still significant. And I think we talk more about that later, and I'm not sure that you need it for the assignment, so I don't want to like go too bonkers. Let me find, that was 4, right? I just want to look at these chat comments, guys. Y always explains for X, Jen, if we're just saying independent and dependent variable. They were just calling the independent Y and calling the dependent X because of where they are on the axis, on those charts, on the axes. But yes, in your R squared, sorry, Why can't I get out of here? In your R squared, yeah, it's always the percentage of the dependent variable that can be explained by the independent variable, always. Otherwise, you've got things backwards in another chat. I should just move this over here. Okay, get it. Okay, awesome. Okay, moving on. So inferential stats. So now we're not talking anymore about just the relationships in general and how they're related, how these two variables are related to each other, but we're making a prediction. We're saying, well, we'll get into it more. Again, we've talked about random samples are the best for these, right? I don't want to go over it, but a random sample, for reasons I think I explained in the first video, is best for any time you're trying to make an inference, right? Because you need that sample to be as representative of the actual population as possible. The closer your sample population is to the target population, the stronger the inference that you make, and it becomes much more statistically significant. And we'll go into that a little bit more. This is pretty much what I just said. There's a chance you'll get a certain was the chance that you flip a coin you will get heads. Probability is proportion of possible outcomes. I don't think you need to talk about probability in this. Did anyone look at the assignment?
Yes.
Did it ask anything about probability? I don't think it does. I just don't want to like confuse you guys. I mean,
Not that I remember.
no, I know. And it's actually, you'll do this in EPI in so much more detail. I kind of just want to not worry about that for now. So random sampling means that every attribute, so let's say we're measuring, our target population is diabetics, just in general, diabetics. We want to get as close to the target population as possible. And so using a random sample means that you will get diabetics of different ages, different genders, different lengths of how long they've had diabetes, and so on. Every one of those attributes or elements or really extraneous variables has an equal chance of being selected and represented in your sample population. That is why we random sample. So because you're random sampling, there's a constant probability of being selected. As you draw people out of the population into the sample, the chances of certain elements and attributes being drawn remains the same as you go. Now, unfortunately, this doesn't necessarily guarantee representativeness, but it's the closest thing that we can get. So the more random your sample, the higher the significance of your inference. Because of this, we want to know that, for example, you have your independent and dependent variable, and as you've made a change in your independent, right? You've done something, and the dependent variable has changed. Something has happened. Well, you want to know that that change in the dependent variable is because of the independent variable, not just because of chance, right? And when you control for all of those extraneous variables, all of the other attributes, then you have less of a chance that that change in the dependent variable is happening just by chance. It's more likely that it's happening based on the independent variable. So you can represent this in a frequency distribution or a polygon. We've talked about this ad nauseum. The area under the curve is 100% of the sample. Sections of the area under the curve are proportions of all cases, blah, blah. We've done this. And the perfect bell curve, we've talked about this. Did everybody do okay on this part with the standard deviation away and blah, blah? Yay or nay?
Yeah, I did okay with that. Did good.
Yeah,
With
me too.
Okay, good. Oh, that's awesome, because a lot of people really struggled with that in my year, which means you guys are awesome. This just a little depiction of it again. We've talked about this. So 1 standard deviation, 2 standard deviations, anything outside of that, any score outside of that is going to be significant, statistically significant. So these z-scores actually really threw me off when we studied it. But basically, because you're not going to use these necessarily in your assignment, because you're going to use a T-score or an F-score, depending on whether you're doing a T-stat or an ANOVA test, right? So I'm not sure why they explain it first this way. I'm sure there's a reason. It's just I don't get it. The score will be somewhere on that curve. Yeah. I honestly don't worry about this, because you're never going to talk about z-scores in your assignment. You're going to talk about your t-score and your F. Let me just see if your z-score is 247 will be in the body. Yes, because it does not have an A plus. Yeah, and it's okay. We're going to go through this with the T and F score. So I just don't want to kind of let's pretend it's not a z-score or z-score. I'm being very Canadian right now. Your score, let's say your score hits right here. You know, it's more than 2 standard deviations away, so it's automatically significant. Actually, it's just confusing the way they're explaining it. I don't like it. Measuring is 1 SD and 700 is with 2 SD. We can use the universal table to tell us what I was getting, say 600. Yeah. We're gonna go over all this with the T-stat stuff. Okay. So a sampling error. There's always a sampling error, right? Because you can't ever have the exact same sample as your target or whatever's happening in the real population. So let's say you did 20 studies from 20 samples, right? There's 20 samples, you did 20 studies with those 20 samples. Each of those studies would have a different mean. Each of those samples would have a different mean, right? So you did, let's look at it here. You did 20 different studies on, let's say, correlation, like the sleep. Oh no, we didn't want to do that one. Trying to think of a cause and effect one. Sorry guys, I usually have time to prep more, but if anybody wants to make one up, let me know, because my brain is like really not working. So you know, say there's like 20 samples of diabetics, and you want to know if this medication is working to, you know, help them. And each of those different samples really is a different study that's done. And then that different study will come up with a different score, right? Some studies might say here, some might say here, some might say wherever, it doesn't really matter. If you put all of those studies together, and then you take the mean of each one of those and you put them together, you have what they call a grand mean. And it's basically just a distribution frequency curve, but instead of being specific scores in a sample, it's actually the mean of all these different samples. So whatever you're studying, if there's been 20, 30, 50, 100 other studies on it, let's say, do vaccines cause autism? There's been 1,000 studies, right? You take all of those studies and you put them together and plot the scores on here. And you want to see, so this is where that, I'll explain that in a second. Sorry guys, it's so confusing. You get a grand mean. So it's the mean of all the other means. And when you do this, if you keep going, you eventually will come up with a normal distribution. This is really important because this is going to fit into, there's a question definitely on the thing. And I know that that's really confusing and I didn't explain it super well, but we'll go over it again. Where the z-score, the z-score comes in, makes much more sense to talk about it here, is because let's say you have 50 different studies on whether or not vaccines cause autism, but they used different ways of measuring that. So their scores are not all going to be, how do you compare them? How do you get a mean when, for example, like one's in millimeters and one's in feet, the other one's in, you know, grams, but they're all measuring the same concept, but they're just measured completely differently. So say with the vaccines and autism, they're all measured differently. That's when you use a z-score, a z-score, sorry. It's a universal X score. So you would take each of those results and convert them into a z-score, which we don't need to know how to do we won't have to do that. But that way you can then put them all onto this distribution chart and get your grand mean of means, okay? This actually, I think, is a typo because it should be standard error, which they're going to ask you about later. Okay, central limit theory. I just have to read that because that doesn't look very. Any shape of your population distribution will generate samples with means that when you put them together will be normal. Yeah, I just said that. Now we can make inferences about probability. Okay. So we can only make an inference about the general population, so all diabetics that we're aiming for, based on the sample population, if we know that it will eventually be evenly distributed. So the fact that the more samples you get, we talked here about you're doing 20 samples from 20 studies, go with the vaccines and autism. I feel like that's a simple one. If you only have 20 studies, it may not look like a perfect distribution curve, right? But what the central limit theory says is that as you continue to generate samples and you get more and more means from those samples, eventually it will become a normal distribution. And you have to know that in order to make an inference about probability. Okay, you can't, yeah, I think that's pretty. So we need, this is all under your central limit theory. In order to make inferences, you need to know that the shape of the mean approaches a normal distribution curve. The grand mean, that doesn't even matter. Variation, the standard deviation of the distribution of the sample means is called the standard error. Okay, so actually I was wrong. So this is a question on the thing, and it was really, I think everybody lost marks for this last semester or whenever I took it. So when we talked the first, like last time we went over, like for the first assignment, we talked about how you have that standard deviation, right? So you have this lovely distribution and you got your 1 standard deviation, your 2 standard deviation. The standard error is basically the standard deviation, but it's the standard deviation when you have, instead of scores, you have a bunch of different studies and you're looking at the means of
all of those different studies. Okay, so if you have, again, 100 studies on do vaccines cause autism, you've compiled them all, you've put them all into a Z-score, so they're all in the same language now, and you come up with a distribution, like a distribution chart like this. You don't use a standard deviation, you use a standard error. What is the expected difference? So this tells you like what the standard error is, measuring how close your group, your sample is to the population that you're trying to measure. So because you're looking at 100 different studies, you're looking at 100 different studies, that then, because there's so many studies, we basically say like that's the population. How close is your sample mean score to the grand mean of all of the other studies that have been done on the same subject? So you can have 1 or 2 standard errors away. So, or 3 or 4, or however many. So the sample goes up, the standard error goes. I know it's so confusing. I know you can see you guys blinking at me, and I'm just like, yeah, that's fine. Because of the assumption that won't matter. So you'll see this later when we go to make our inferences. We use a standard table. I think in this case they're talking about the Z-score table, but there's a T-score table, there's an F-score table. The only reason we can use this table is because we know that there is a connection between a random sample and a normal distribution. So just, that sounds confusing, but it's just what we were saying up here. We know that the more samples or studies we collect, the closer it will be to a normal distribution, which means we can use the universal tables because that's what the universal tables are based on. Poof. Okay, awesome. This stuff's hopefully a little better. So hypothesis testing, basically we don't do this in descriptive statistics. We only do this in inferential statistics. It uses sample data to evaluate a hypothesis about a population parameter. So what is going to happen after treatment is administered? We want to say, well, you know what, don't worry about these drawings. I put a lot of extra stuff in my notes, guys. So I don't want you to feel like you're missing out on stuff. I just don't want to overload if we don't need to look at it. So there's these 7 steps of hypothesis testing. You're going to do these in your assignment. They are broken down in the assignment. You have to state the null or research hypothesis, what test stat you're going to use. You're going to use a T, you're going to use an R, whatever it is. We'll go through these on the thing. Oh, the degrees of freedom. Ugh. Are you guys sure you got to ANOVA already? You're not even awake, are you guys?
I'm awake. Sorry, I didn't even look at the stuff yet.
No, we haven't got to ANOVA. No.
Yeah, we didn't discuss that yet.
I feel like it's on this assignment though.
Yes, it is.
Okay.
Maybe it was supposed to be last Saturday, but we didn't have.
Oh, right. We talked about this. It's because you're a week ahead. Whew. How are you guys understanding everything we've gone over so far? Is it making sense? Because I'm kind of like making it make sense to myself as I'm telling it to you because I haven't looked at this stuff in so long. So it's a little bit less like put together than I usually am. But is it making sense?
Yes, it does. But I still have to go over and try to, for me, to understand it again. But
And
as
honestly,
you were talking about it, I'm understanding it.
okay, good. And honestly, that's how I did my assignment. Every single question, I went back to my
Right.
notes and went through and said, okay, they're asking me for what is a standard error. And I went back and I talked through all of this to myself and then answered the question basically.
Right.
And so, yeah, like the first time through, it does kind of feel like, whoa, but the more you do it in the assignment, I think that the better it's going to be. And hopefully hopefully I think we're okay so far. Like I've understood everything so far, so that's good. So your null hypothesis. Okay, so this is really important to know. A null hypothesis is what you start with in every hypothesis testing sample, whatever that you're doing. You start with the null hypothesis, and the null hypothesis says the independent variable has no effect on the dependent variable. So if you have a question about vaccines and autism, and the null hypothesis is vaccines have no effect on autism, right? Usually this isn't stated in the project, but you're going to do it in your assignment. Then you're going to have your alternate or research or scientific hypothesis, which for, let's say for anti-vaxxers would be, hopefully I'm not ruffling any feathers over there, would be whatever, your nurses. Yeah. So, vaccines cause autism. Okay, that would be your alternate or research hypothesis if you were an anti-vaxxer. So you're going to take, and then your Z-score, we talked about this, right? It's your sample mean minus the hypothesized population mean divided by the standard error between. Do not worry about that. That is so confusing. Don't even worry about it. I think it is, Marianne. I think the ANOVA is, but we'll look at it as we go, and I won't go over it in the notes, but if it's there, I'll go back. So if you reject the null hypothesis, this means that your sample mean, so you've done this test on whether or not this medication works for diabetes. Say this magical new medication doesn't work. Well, in all of the other hundreds of tests that have been on, measuring diabetic success or whatever, you've got all those means kind of, oh, I should draw this. It's just, sorry, give me a second. So you've got, a grand mean from all of those studies, and, you have all the other means from the studies, which would be like all over, right? But this is your grand mean, and that's what matters. You have your standard error, your 1 degree of standard error, which is here, or a straight line. Your 2nd degree of standard error, which is here. But your little test that you did with this brand new medication actually scored over here, right? It is outside of 2 standard errors or 2 standard deviations, if you want to think of it that way. I like to think standard deviations, even though it's wrong. This is a significant score. And why? Because we know that 95% of scores in a normal distribution, 95% are gonna land within these 2 standard deviations, or in this case, 2 standard errors from the mean. If your score lands out here, it is statistically significant. And then you will also have a p-value on this, which we'll worry about later. It just tells you the probability of getting that, and that'll come in the next section. Does everybody understand that? This is really important to understand, because this is the basis of all of your inferential statistics that you're going to be making on the whatever. Standard error is not the same as standard deviation, only because you use standard error when you're talking about comparing means from different samples and different studies, right? You have, you know, this study on diabetics showed the average sugar to be here. This study showed it here. This study showed it here and here and here and here. And there's 100 of those studies. You come up with a grand mean from those studies. And this is your grand mean, right? Because we're talking about a group of studies, not necessarily scores in one study, right? Those means from each one of those studies, the mean, we did the mean, median, mode for each one of those studies. The mean becomes your score, basically, right? And then you make a grand mean based on that. And because you're doing that, we call it a standard error and not a standard deviation, because we want to know how far the population is from that mean. So this mean here then, sorry, my kids are going to be driving us crazy. So this mean then, really what it's telling you is this is the standard. This is the norm where the population is. I swear I'm going to disown him. Can you guys see all that? Freaking kill me. So, right, this is where most of the population is. If your score, after you did your test with your magical new drug, falls, sorry guys, just hang on. I got it. For Pete's sake. Okay, so let's say your score lands here. Well, I mean, this is the average. So it's not even a whole standard error or standard deviation, whatever, away from that average. So it's really not statistically significant at all. But if your score lands over here, it's in that 5%. And we talked about this before, right? You've got the 2.5% on this side and your 2.5% on it's really hard to do this, 2.5 on this side. So because it's a two-tailed test, and we'll talk about that later too. This is outside of two standard errors, which means it's this much further away from the average or from what is already happening, which means it's significant. Yeah, you should be sorry. Does that help, or does that confuse things? So standard deviation is for one study, yes, and standard error is for the central limit theory. So standard deviation, yes, is for one study when you have 20 different scores in one study. So you've done that study on diabetics and all your blood sugar scores, and then come together, you make this thing, and you figure out what your mean is, and then that's the mean of your study, and you send that study out there into the world. Somebody else comes along and does another study. They want to know if their results are actually significant, if it matters. So they take the means of all of the studies they can find, and then we use standard error. And yes, we use it for inference and prediction. And it's going to make more sense as we go on and do the T-stats, because we're going to do this like 100 times to explain it. So if you still don't have it, if you don't have it right now, that's fine. But if you don't get it at the end of the next two, then we'll go over it again. Sorry. that was 6, right? Okay. All right. Let's talk about t-tests. There are 2 types of t-tests. One is for 2 independent samples. The other is for 2 related samples. We're going to tell you the difference between those 2, I think, later. So let's not worry about it. Again, you've got your steps of hypothesis testing, which it's exactly the same as what we did on the last page. So how do you decide if you're going to run a t-test or not? Well, so a t-test compares the difference between two groups, the mean difference. So is the difference, and I know it's just words right now, but it will make sense. Is the difference more than you would expect from chance alone? So, there's always going to be difference between groups. So let me explain what I mean by groups. You have 2 different groups of people. You're doing a randomized control trial, and you have groups of people who have taken a medication and groups of people who have not taken a medication. You want to compare those 2 groups. You want to compare the scores of those 2 groups. Let's go with blood sugar again, just for the heck of it. It seems simple. So you have group A who did not take the medication, or they took another medication, right? And you have group B who did take this new medication that you're testing, and their scores are higher or better, or lower, I guess in this case. Their blood sugar is lower. It's better. You want to know, okay, what are the chances of that happening just by chance? And then what are the chances that that has happened because of that new medication? What are the chances that that has happened? The change, again, it's the same as that R, we talked about R squared, right? What are the chances that the change in that dependent variable, in this case, the blood sugar, can be attributed to the independent variable or the new medication? And what are the chances that it's just by chance that those scores are different, okay? Now, obviously, even if the null is true and there is no relationship between this new medication and the better scores, you're still going to have some difference between the 2 groups, right? Because you're not going to have the exact same numbers. But is the difference big enough that it's not likely that chance alone is what caused that change in the dependent variable? So again, remember we talked earlier about the R squared. It's the same thing. We're trying to decide what's the chance that it was the outcome of this is based on the independent variable. What's the chance that it's just a fluke, right? So again, don't worry about this because it's just confusing. Population of SD. So t-score is same as it, except that it uses an estimation of variation instead of yes. Okay, you don't need to know that. This is going into like how the t-score is calculated, and you don't have to do that math. The Excel is going to do it for you. So I didn't have to write that down, but I did. So remember we were talking about a universal table, and the only way we can use that universal table is if we know that things are in a normal distribution. This is one of those tables. This is the T table. And what it is it's a list of all the possible scores that the T-stat could have dependent upon degrees of freedom and the level of measures set for the test. And that might not make sense right now, but it will. So if the degrees of freedom is set at greater than 100, then you'll see this is better explained in the actual chart. So I'm just gonna, this explanation of degrees of freedom, I'm gonna go through it, but I'll go through it quickly because you'll understand it more when we do the ANOVA. It's way easier to understand there, but let's just go through it. If you don't quite get it right now, that's okay. So no matter what you're measuring, there's always going to be differences in scores. Let's go back to our diabetics. We've got, 100 scores of blood sugars. Obviously, they're not all going to be 4.3, right? They're all going to be different. You're going to have variation. So when you observe a score, right? You measure that blood glucose and you get that score. You can't ever know, and we talked about this in research, you can't ever know that that's a true score, right? So degrees of freedom is just a concept that tries to acknowledge this kind of variability in the numbers. So there might be something going on in the study that has nothing to do with the study procedure, but that's still affecting those numbers. Whatever, it's making allowance for error, for a little bit of sample error or whatever. So it makes an adjustment on the distribution to make it a little bit harder to achieve statistical significance. Okay, so when we have our little distribution curve here, and we've got our mean and our standard, right? And our t-score comes out here. That score, depending on your degrees of freedom, okay, so if your degrees of freedom are 2, that score has to be, I'm just going to make up numbers based on blood glucose, okay? So it's not like, that score has to be less than, let's say it has to be less than 6 in order to be on this side, okay? But if your degrees of freedom are 5, that actually changes this number, and this will make more sense later, I promise. It changes that number and says, well, actually, in order to be outside of these regular, to be statistically significant, the score has to actually be 4. So it's much harder to land in this statistically significant area because you have to have an even lower score or higher, depending on what you're measuring. For us, CBG, we want it to be lower, right? Again, that'll make more sense as we go. So again, in our sample, we're going to acknowledge that all scores vary from one to the other. But this way we can reduce that a little bit by adding in these degrees of freedom. And when you look at those charts that we talked about the T-stat chart. I don't know if anyone has, sorry, I wish I had a copy of it. It basically, you match it up based on degrees of freedom. So like your degrees of freedom are here and your T's are here, and you match it, and you'll see this. You match it up. So if your degrees of freedom are this, the number needs to be this. If your degrees of freedom are here, the number needs to be this. And I understand that that's kind of out there, but it will make sense when you look at the chart and also when we get there. So if you know the sum of all scores in the sample, one score must be, you don't need to understand all of that. So the degree to which each score is free to vary or differ. So if you're saying, a CBG of 4, let's allow that to be, it could be 4, but it could be, 3 or 5, whatever. So you're giving it 1 degree of freedom on either side, right? Don't worry about this stuff. And here we go. So this is actually a really good way of showing this. So if your degree of freedom is 5, your distribution curve looks like this. So again, here's your mean. Sorry, my lines are all crooked. Let's do this. So, okay, that's not good. Sorry, just seeing the way that it's here. So this is your mean. And then I think this might work better. Who, God only knows. When you're following this line here, which is your degrees of freedom 5, it's a little bit easier to land here. right? But if you put your degrees of freedom at 20, you can see that it raises the peak of, honestly, you don't necessarily need to know this, but it makes it a lot harder for you. I didn't draw it well enough, but it makes it a lot harder for you to land in that spot. It's going to make more sense. So basically, it changes the point at which your critical score can occur in order for you to reject or accept the null. So if your critical score, which is what you're going to get when you perform your t-test, you're going to get a critical t-score. And where that critical t-score sits on this distribution is going to tell you whether or not it's significant. If it sits here, it's within that 95%. It is not significant, so you're going to accept the null. There is no relationship between these two things. But if your score lands over here, it is, and this is actually wrong. This should be 2.5 and 2.5, but whatever. It is statistically significant. It's within the 5% that's outside of the two standard deviations or two standard errors, which means whatever your independent variable was, in this case, a new medication, it actually did affect the dependent variable, which means you're going to reject the null hypothesis because obviously there isn't no relationship because one is affecting the other. Is that getting more clear as I've gone over it like 3 times, or am I spinning you guys out? Gotta answer me, guys.
It's good.
Okay. I have to just make sure because I'm like, sorry. So your p-value, we've talked about, your p-value is related to this as well, right? When we say we have a p-value of 0.5, that's what this is talking about. 0.5 means 5%. It's within the 5% that is outside of this average range or whatever. Sorry. Oh, less stringent. Okay, that makes sense. So if you change your degrees of freedom or whatever, it actually moves this line to where, let's say it's here now. So this isn't necessarily statistically significant. It just makes it a little bit more stringent. So your p-value in this case is no longer 0.5, it's 0.3, which is it's awesome because if you have a study with a p-value of 0.3, it means it's very statistically significant. But you don't have, like 0.5 is enough. We'll go over that. So how do you know when you do a t-test, you come up with this critical t value, okay? So you have a value of, let's go, I don't know. So 1, let's just do this. 3. I'm doing this with the mouse, so it's really, sorry, it's so messy. 6, 7, 8, okay? You come out and your p-value comes out as, or sorry, your t-value comes out as 6.4, let's say. Okay, that's your critical t-value. That is where, so that falls where? Let's say it falls right about here on the thing, right? If that t-value is inside of that 5%, so like out here, right? Let's say it's right on that line. That means it has a p-value of 0.5 or 5%, right? But let's say it's way the heck over here. Let's say the mark is actually 7, right? sorry, the T stat is actually 7, your critical stat. Well, that puts it, if this is a p-value of 0.5, because this 0.5 represents, you know, the 95% that are in here, and then the 5% that are out here. Well, we don't want to just say it's a p-value of more than 0.5. You want to know what the heck that p-value is, because it's going to raise the significance of your results, right? So you would use this chart to tell you, it'll tell you this is where the critical region is, right here. Depending on the degrees of freedom, it's going to tell you where this line is. And then you decide where your score falls and whether it's higher or lower. If it's higher, it's more it's statistically significant. If it's lower, it is not statistically significant, unless it's lower over here, which means you've done something really rotten in your study. Don't worry about that. Okay, so remember I said there's 2 different types of t-tests. There's an independent sample t-test and a related or dependent samples t-test. Don't, you know what, eventually this is confusing, so don't worry about that. What did we call them up here? Independent and related. Okay, I like that. So you've got independent samples, 2 completely different groups of people, and you want to test, okay, let's say you have 2 different groups. You have RNs and RPNs, and you want to test their level of collegiality or whatever it is on your thing, right? You've got 2 separate groups of people. They're independent samples, 2 independent samples of people, okay? Sorry, don't worry about this stuff for a second. If it's the other kind of a t-test is the related samples t-test, and I think that's what it's called up here, right? They're 2 related samples. And so basically what you use this for is if you do, what you'll use it for is for like pre and post, right? So you actually have, it's basically the same sample. It's all RNs, but you want to see what their collegiality score is before they do a workshop and after they do a workshop. You can't use this because you don't have 2 independent samples. You have to use this because you're using 1 sample group, okay? So in order to use the independent samples t-test, your independent variable, and again, this is you as you're going through your assignment, you're going to flip back to these notes, which I'll send you, and you're going to go, okay, because you're going to decide, should I be doing a t-test? Well, is the independent variable categorical? Yes, here it's RNs and RPNs. Whether we want to call that nominal or ordinal, whatever, but it's definitely categorical. And then the dependent has to be continuous. So we're measuring collegiality scores on a scale of 1 to 10. That's an interval or a ratio depending on how it's worded. And so it meets those 2 criteria. Homogeneity of variance just means that the variance between the groups are not too different. You don't need to worry about this because in this course, they're always going to be. And what that basically means is that you have RNs and RPNs, and not all your RNs are over 50 and all your RPNs are 20 to 25, right? They're completely different. The variances is like all over the place. Yeah. When all 3 of these assumptions here, right? When all 3 of these assumptions are met, I don't know what that means, pooled formula, so honestly, sorry. Oh, you use a different and a smaller t, but again, you don't need to worry about this because that's not going to happen. You're going to use this, which is the formula that comes out in this, this chart here that we were talking about with the t-tests, and it'll tell you where it's going to tell you where to draw this line on your chart. It's because it's a formula that you can use because you meet all of these criteria, Okay. Okay, here. So again, that was for your independent samples t-test. For your related samples, you've got, this is what you're going to work with probably, pre-test, post-test. It could also be two groups of people who have some similar attribute. Oh, and again with the biological twins, but we're not going to do that. The sample must be matched, random, greater than 30. Small sample sizes are like a really good thing to talk about in all of your assignments, because it's not a huge sample size. So a lot of this is not necessarily generalizable. And the significance, you might have a high significance, but that doesn't necessarily mean that it's like generalizable to the population because you have such a small sample. Whew. So we've talked about this. This is your pre-test, post-test. It's the most common. Okay, when you're reporting your t-test results, you're going to do this in your assignment. So you're going to state the type of t-test that you did. So an independent t-test was done, or a paired. So the related, I believe in Excel, it's called paired. We'll look at it when we go to kind of figure that out later. But the type of t-test is independent, one-tailed, or two-tailed. We'll talk about that again later. You're going to state the t-value, right? This is the critical t that I came up with. The degrees of freedom, where on the distribution curve that t-value sits, that will be described by your p-value, right? If I say to you, the t-value was 162 at a p-value of 0.3. If your p-value is 0.3, you know where it's sitting on this curve, right? It's definitely sitting outside of this 0.5 or the 5%. It's actually in 3%. So you're also going to state, so you're going to state your t-value, your degrees of freedom, your p-value. So that's telling you where it's sitting on here. And then your mean, your standard deviation, and your sample size for each group. Core values of central tendency and variability. I don't think you do that in the assignment, but it's okay. So, oh, look at this. We broke this down. That's nice. So this is awesome. You'll have these instructions in your notes. This is just how to do it. You go to the data analysis tool pack. You decide whether it's going to be a independent, and then assume equal variances, or a paired sample. Yep, which is all. You're going to set the alpha at 0.5. We'll talk about that later, I think. If you're doing a pre-test, post-test, yeah, good. Okay,